Welcome to the Cisco NetAcad CCNA3 Enterprise Networking Security and Automation lecture series. This is our first lecture for this course, and if you haven't seen my previous lecture series covering CCNA1 and CCNA2, I will leave links in the description for those playlists. I would recommend that you go through previous CCNA lectures before moving forward with this CCNA3 course. Today, I will cover module number 1, which is Single Area OSPF version 2 concepts. The primary objective of this module is to explain how Single Area OSPF operates in both point-to-point and broadcast multi-access networks. We will cover OSPF features and characteristics so that you can describe the basic OSPF features. We will cover OSPF Packets and OSPF Operation. OSPF features and characteristics. So the OSPF stands for the Open Shortest Path First Protocol, which is a family of IP routing protocols, and it is an interior gateway protocol, also known as IGP, for the internet, which is used to distribute IP routing information throughout a single autonomous system, also known as AAS, in an IP network. As we go through this course, we will get into the details of how you can set up an OSPF network and how the Open Shortest Path First protocol act on different configurations. So the OSPF is a link state routing protocol that was developed as an alternate for the distance vector routing information protocol, also known as REP. OSPF has significant advantages over REP in that it offers faster convergence and scales to much larger network implementations. So the OSPF is a link state routing protocol that uses the concept of areas. The network administrator can divide the routing domain into distinct areas that help control routing update traffic. A link is an interface on a router, a network segment that connects two routers, or a stub network such as an Ethernet LAN that is connected to a single router. Information about the state of a link is known as a link state. All link state information includes the network prefix, prefix length, and cost. This module covers the basic single area OSPF implementations and configurations. So what are the components of OSPF? All routing protocols share similar components. They all use routing protocol messages to exchange route information. The messages help build data structures, which are then processed using a routing algorithm. Routers running OSPF exchange messages to convey routing information using 5 types of packets. Those are hello packets, database description packet, link state request packet, link state update packet, and link state acknowledgement packet. These packets are used to discover neighboring routers and also to exchange routing information to maintain accurate information about the network. In this course, it is important that you understand what each of these packets do. So we'll go over that in a little bit of more detail in next few slides. So you need to understand how OSPF hello packet is different from the database description packet and different from the other link states packets. So you should be able to differentiate and understand the functions of these packets as we go through these lectures. OSPF messages are used to create and maintain 3 OSPF databases. They include adjacency database, link state database, and forwarding database. The adjacency database has a table called the neighbor table, and it lists of all neighbor routers to which a router has established bi-directional communication. This table is unique for each router and can be viewed using show IP OSPF neighbor command on your Cisco routers. So if you have a Cisco router with OSPF setup, you can run the show IP OSPF neighbor command, and that will get you the table for the adjacency database. The next database is the link state database, also known as LSDB, which is a topology table that lists information about all other routers in the network. The database represents the network LSDB. All routers within an area have identical LSDB, the link state database, and can be viewed using the command show IP OSPF database. So if you have a Cisco router, you can run the show IP OSPF database, and that will give you the LSDB. The forwarding database contains the routing table. That includes a list of routes generated when an algorithm is run on the link state database. Each router's routing table is unique and contains information on how and where to send packets to the other routers. This can be viewed using the show IP route command. So if you have a Cisco router, you can run the show IP route command with the OSPF setup, and you can view the forwarding database. So the forwarding database have the routing table, and those list of routes are generated using an algorithm that is, when it is run, based on the that link state database. So it is, this database routing table is built on the database from up here. The router builds the topology table using results of calculations based on the Dijkstra's shortest path first algorithm, also known as SPF algorithm. The SPF algorithm is based on the cumulative cost to reach a destination. The SPF algorithm creates an SPF tree by placing each router at the root of the tree and calculating the shortest path to each node. The SPF tree is then used to calculate the best routes. OSPF places the best routes into the forwarding database, which is used to make the routing table. So that's the process of creating the routing table. It's used the SPF algorithm. So that's a key component of the OSPF. Link state operation. To maintain routing information, OSPF routers complete a generic link state routing process to reach a state of convergence, because the main purpose of using a protocol like OSPF is for faster convergence. So this is one of the primary functions. The following are the link state routing steps that are completed by a router. It establishes neighbor adjacencies. It exchanges link state advertisements. It builds the link state database. It executes the SPF algorithm. Then it will choose the best route. So these are the steps that needs to go through to create the link state, the routing information. Single area and multi-area OSPF. To make OSPF more efficient and scalable, OSPF support hierarchical routing using areas. An OSPF area is a group of routers that shares the same link state information in their LSDB. So if somebody asks you, what is an OSPF area? That is the definition of an OSPF area. So OSPF area is a group of routers that shares the same link state information in their LSDB. OSPF can be implemented in one of the two ways. That includes single area OSPF, where all routers are in one area, which comes with the best practice with the use of area 0. or the multi-area OSPF, where OSPF is implemented using multiple areas in a hierarchical fashion. All areas must connect to the backbone area known as typically the area 0, and routers interconnecting the areas are referred to as area border routers, also known as ABRs. You will hear that term and these concepts a lot as we go through this lecture series. The focus of this module is on single area OSPF version 2. So while the focus of this module is the single area OSPF version 2, as we go through this lecture series, I may cover topics that are related to multi-area as well. Multi-area OSPF. The hierarchical topology design options with multi-area OSPF can offer the following advantages. Smaller routing tables. Tables are smaller because there are fewer routing table entries. This is because network addresses can be summarized between areas. Route summarization is not enabled by default. Reduce link state update overhead. So designing multi-area OSPF with smaller areas minimize the processing and memory requirements of each of those routers. Reduce frequency of SPF calculations. The multi-area OSPF localize the impact of a topology change within an area. For instance, it minimizes routing update impact because LSA flooding stops at the area boundary. OSPF version 3. So the OSPF version 3 is the OSPF version 2 equivalent for exchanging IPv6 prefixes. OSPF version 3 exchanges routing information to populate the IPv6 routing table with remote prefixes. So this is a key information that you should remember. The OSPF version 3 is for IPv6 routing. Note, with the OSPF version 3 address families feature, OSPF version 3 includes support for both IPv4 and IPv6. OSPF address families is beyond the scope of this curriculum. So general OSPF version 3 is for IPv6, but OSPF version 3 with address families feature will enable you to use OSPF version 3 for both IPv4 and IPv6, but we will not cover that in this lecture series. OSPF version 3 has the same functionality as OSPF version 2, but uses IPv6 as the network layer transport, communicating with OSPF version 3 peers and advertising IPv6 routes. OSPF version 3 also uses the SPF algorithm as the computation engine to determine the best paths throughout the routing domain. OSPF version 3 has separate processors from its IPv4 counterpart. The processes and operations are basically the same as in the IPv4 routing protocol, but run independently. So that's all you need to know about OSPF version 3 for now in this class. OSPF Packets. There's a video called OSPF Packets that nicely laid out how this OSPF works with the hello packet database description, the link state requests, etc., etc. If you do not have a copy for this video through your Cisco NetAcad or through your academic institution, I will post a link in the description for this video, as well as a card on the top right hand corner, so you can go ahead and click on it on my YouTube channel so you can watch it. I would recommend that you watch this video before you move forward, because that will give you a basic idea about what we're about to cover. Types of OSPF packets. So this table summarizes the 5 different types of link state packets, also known as LSPs, used by OSPF version 2. The OSPF version 3 has similar packet types, but we won't be covering that in this module. So if you have watched the previous video that I mentioned, you can watch on my YouTube channel or through your NetAcad, Cisco NetAcad. You probably came across the hello packets, the database description, the link state request, the link state update, and the link state acknowledge. So the hello packet discovers neighbors and builds adjacencies between them. It's like saying, hello, these are my information, things like communicating between the devices, neighbors. So it's just like saying hello to someone, So the database description, or DBD, checks for database synchronization between routers. The link state request, also known as LSR, requests specific link state records from router to router. Link state update, also known as LSU, sends specifically requested link state records. Link state acknowledgement, also known as LSARC, acknowledges the other packet types. So this basically acknowledges the receiving of these packets. Link state updates. LSUs are also used to forward OSPF routing updates. An LSU packet can contain 11 different types of OSPF version 2 LSAs. OSPF version 3 renamed several of these LSAs and also contains 2 additional LSAs. LSU and LSA are often used interchangeably, but the correct hierarchy is LSU packets contain LSA messages. So that's a key important thing that you should remember for your exam. LSU and LSA are often used interchangeably. However, for your exams and for understanding the concepts, you need to realize that the correct hierarchy is LSU packets contains LSA messages. So on the right hand side, it shows some information about LSUs and LSAs. So basically, LSUs includes hello, DBD, LSR, LSU, and LSARC. And within the LSU, you will have the LSA information. So remember that the LSU packets contain the LSA messages. So let's look at the hello packet. So the OSPF type 1 packet is the hello packet. Remember from our previous slide with the table, which has 1, 2, 3, 4 on the side, I believe. And so the first, the type 1 packet is also, the hello packet is also known as the OSPF type 1 packet. Hello packets are used for the following: to discover OSPF neighbors and establish neighbor adjacencies, advertise parameters on which 2 routes must agree to become neighbors, elect and designate router, also known as DR, and backup designated router, or BDR, on multi-access network like Ethernet. Point-to-point links do not require DR or BDR, so it's for multi-access purposes. It will also, the hello packet will be used for DR and BDR designations. So on the right hand side, we have this diagram that you probably have seen if you watched that video, that the external video from Cisco that I have posted to my YouTube channel. And it shows the OSPF packet header and the OSPF packet type specific data which contain the hello packet. And this is what the breakdown of the OSPF packet header and the hello packets, what it look like. So you have the hello interval, and you have an option, and then you have the route priority and then the interval and all the other information associated with the OSPF hello packets. And you can see that on this diagram. And for your exams and quizzes, you probably don't need to know everything in here. However, if you want to be good at what you do, and if you want to understand the concept of OSPF, you should be able to understand what's shown on here, right? So as we go through this course, I know this is the very first lecture right now, but as we go through this course, you will have a complete understanding of how these packet headers and the packet information are important to OSPF routing. Okay. So for now, just know this is basically how it look like. OSPF operation. There's another video called OSPF Operation, which I'll be covering in next few slides. If you have access to this video through Cisco NetAcad or through your academic institution, you can go ahead and watch them. Or I have a copy of that video posted to my YouTube channel, and I will leave a link in the description as well as a card on the top right hand corner. And again, watching these videos will enhance your understanding of concepts that we will cover in next few slides. OSPF operational states. Down state. So the down state is no hello packets received. That means it is down. The router sends hello packets. Transition into the init state. So if there are no hello packets received, the router sends hello packets. However, it will eventually go into the transition into init state. Init state. Hello packets are received from the neighbor. They contain the router ID of the sending router. Transition to two-way state. Two-way state. In this state, communication between the two routers is bidirectional. On multi-access links, the routers elect a DR and BDR. Remember, area border routers. So transition that at this stage into EX start or X start state. So the X start state, at this stage, what happens is on point-to-point networks, the two routers decide which router will initiate the DBD packet exchange and decide upon the initial DBD packet sequence number. Exchange state. Routers exchange DBD packets. If additional router information is required, then the transition into the loading, otherwise transition into full state. So the loading state would happen if the additional information is required. It has the LSR and LSUs are used to gain additional route information, and the routes are processed using the SPF algorithm as expected, as we are in OSPF, which uses the SPF algorithm, and transition at this point once it obtained that information into full state. So it could go from exchange to full state, exchange state to full state, or it could go from exchange state to loading state to full state. At full state, the link state database of the router is fully synchronized, and the OSPF operation in here has been completed. Establish neighbor adjacencies. To determine if there is an OSPF neighbor on the link, the router sends a hello packet that contains its router ID out all OSPF enabled interfaces. So to determine there is an OSPF neighbor on the link, what the router going to do is going to send that hello packet that contains its router ID out all of its OSPF enabled interfaces. The hello packet is sent to the reserved all OSPF routers IPv4 multicast address of 244.0.05, because in OSPF configuration, this would be the multicast IPv4 multicast address for all OSPF routers 244.0.05. Only OSPF version 2 routers will process these packets. The OSPF router ID is used by the OSPF process to uniquely identify each router in OSPF area. A router ID is a 32-bit number formatted like an IPv4 address and assigned to uniquely identify a router among OSPF peers. When a neighboring OSPF enabled router receives a hello packet with a router ID that is not within its neighbor list, the receiving router attempts to establish an adjacency with the initiating router. So that's how the neighbor adjacencies work. So in the next page, we will look at how the process working in a little bit of more detail. So the process routers used to establish adjacency on a multi-access network. In this case, we're going to have these 4 steps. The down init state. So when the OSPF version 2 is enabled on the interface, the R1 transitions from down to init and starts sending OSPFv2 version 2 hellos out the interface in an attempt to discover neighbors. In the init state, when the R2 receives a hello from the previous unknown router R1, it adds the R1's router ID to the neighbor list and responds with a hello packet containing its own router ID. The two-way state, R1 receives R2's hello and notices that the message contains R1 router ID in the list of R2 neighbors. R1 adds R2's router ID to the neighbor list and transitions to the two-way state. If R1 and R2 are connected with a point-to-point link, they transition to X-start state. If the R1 and R2 are connected over a common Ethernet network, the BDR election process will occur. Elect the DR and BDR. The DR and BDR election occurs where the router with the highest router ID or the highest priority is elected as the DR and the second highest is the BDR. So area border routers, right? Remember the DRs and BDRs we covered in previous slides. So this is the backup, this is the primary. Synchronizing OSPF databases. After the two-way state, routers transition to database synchronization states. This is a 3-step process. So those steps includes decide first router. So the router with the highest router ID sends its DBD first because it's the one that's going to get precedence. Exchange DBDs, so as many as needed to convey the database. The other routers must acknowledge each DBD with LSR packet. That's the acknowledgement packet, remember? Send an LSR. Each router compares the DBD information with the local LSDB. With the DBD has more current link information, if the DBD has more current link information, the router transition into the loading state. Yes, this will show up on your exam, so make sure you know these concepts. So I'm just quickly going through some of the lectures, but I will give you a more comprehensive idea about how they work on a real live lab demonstration as well. But remember these steps, it does matter for your exams. So after all LSR have been exchanged and satisfied, the routers are considered synchronized and in a full state. And then the updates are sent, which are LSUs. So when an exchange is perceived, an incremental updates would happen and about every 30 minutes. So that is the synchronization of OSPF databases. The need for a designated router or DR. Multi-access networks can create 2 challenges for OSPF regarding the flooding of LSAs as follows. Creation of multiple adjacencies. Ethernet networks could potentially interconnect many OSPF routers over a common link. Creating adjacencies with every router would lead to an excessive number of LSA exchange between routers on the same network. So it's going to create more overhead. Extensive flooding of LSAs. The link state routers flood their LSAs anytime OSPF is initialized or when there is a change in the topology. This flooding can become excessive as well. LSA flooding with a designated router or DR. An increase in the number of routers on a multi-access network also increases the number of LSA exchange between the routers. This flooding of LSAs significantly impacts the operation of OSPF. If one router in a multi-access network had to flood and acknowledge all received LSAs to all other routers on that same multi-access network, the network traffic would become quite chaotic. So that is really bad. So on multi-access networks, OSPF elects a designated router, also known as DR, to be the collection and distribution point for LSAs sent and received. A DBR is also elected in case the DR fails. All other routers become DR others. A DR other is a router that is neither the DR, which is a designated router, nor the BDR, the backup designated router. Please note the DR is only used for the dissemination of LSAs. The router will still use the best next hop router indicated in the routing table for forwarding all other packets. So the DR, which is a designated router, or if it fails, the BDR will only be used for decimation of the LSAs. It doesn't use for all other packets. It's just for the LSA messages or the packets, right? So that would bring us to the end of this lecture. And now I will go over a summary of what we have covered. We learned that Open Shortest Path First, also known as OSPF, is a link state routing protocol that was developed as an alternative for Distance Vector Routing Information Protocol, also known as RIP. OSPF is a link state routing protocol that uses the concept of areas for scalability. A link state is an interface on a router. A link is also a network segment that connects two routers or a stub network such as Ethernet LAN that is connected to a single router. All link state information includes the network prefix, prefix length, and cost. All routing protocols use routing protocol messages to exchange route information. The messages help build data structures, which are then processed using a routing algorithm. Routers running OSPF exchange messages to convey routing information using 5 types of packets. They include the hello packet, the database description packet, the link state request packet, the link state update packet, the link state acknowledgement packet. OSPF messages are used to create and maintain 3 OSPF databases. They include the adjacency database, which creates the neighbor table. The link state database, which also known as LSDB, creates the topology table. And the forwarding database, which creates the routing table. The router builds the topology table using results of calculations based on the SPF, which is the shortest path first algorithm. The SPF algorithm is based on the cumulative cost to reach a destination. In OSPF, cost is used to determine the best path to destination. So we use the cost as the calculation key for determining the best path for destination. We also learn to maintain the routing information. The OSPF routers complete a generic link state routing process to reach a state of convergence. Establish neighbor adjacencies, exchange link state advertisement, build the link state database, execute the SPF algorithm, choose the best route. So those are the basic steps that it takes and use. With single area OSPF, any number can be used for the area, but however, it is the best practice to use area 0 with single area OSPF. With multi-area OSPF, one large routing domain can be subdivided or divided into smaller areas to support hierarchical routing. Routing still occurs between the areas, also known as inter-area routing. While many of the processor invasive routing operations such as recalculating the database are kept within that area. OSPF version 3 is the OSPF version 2 equivalent for exchanging IPv6 prefixes. And recall that the IPv6, the network address is referred to as the prefix and the subnet mask is called the prefix length. OSPF uses the following link state packets, also known as LSPs, to establish and maintain neighbor adjacencies and exchange routing updates. And we learn about the hello, DBD, LSR, LSU, and LSARC, and I mentioned that it is 1, 2, 3, 4, 5. So it's, you can say, it's a type 1. If somebody says it's a type 1 OSPF packet, it is a hello packet, for example. LSUs are used to forward OSPF routing updates such as links changes. Hello packets are used to discover OSPF neighbors and establish neighbor adjacencies, advertise parameters on which two routers must agree to become neighbors, and elect the designated router, also known as DR, and backup designated router, also known as BDR, on multi-access network like Ethernet. Point-to-point links do not require DR or BDR. We also learned some important fields in the hello packet types are the router ID, area ID, network mask, hello interval, router priority, dead interval, DR, BDR, and list of neighbors. And I showed a diagram of that, the packet on the screen. But that video, the complimentary video that I have posted from Cisco, that also go into depth of looking at those that packet and pulling apart that packet and try to explain that to the students how that packet works. So I would recommend that if you don't remember, or like I went too fast with this lecture, you can go ahead and watch that video to understand and get a better handle of the configuration of the hello packet. The states that OSPF progresses through to reach convergence are down state, init state, two-way state, xstart state, exchange state, loading state, and full state. And we learned that when OSPF is enabled on an interface, the router must determine if there is another OSPF neighbor on the link state by sending a hello packet that contains its router ID out all OSPF enabled interfaces. The hello packet is sent to the reserved all OSPF router IPv4 multicast address, which is the 244.0.05. However, only OSPF version 2 routers will then process these packets. When a neighboring OSPF enabled router receives a hello packet with a router ID that is not within its neighbor list, the receiving router attempts to establish an adjacency with the initiating router. After the two-way states, routers transition to database synchronization states, which is then 3 steps a process, right? Multi-access networks can create 2 challenges for OSPF regarding the flooding of LSAs, the creation of multiple adjacencies, and extensive flooding LSA. So that's the multi-area networks can create. So one of the challenges with multi-area network OSPFs. We learn a dramatic increase in the number of routers also dramatically increases the number of LSAs exchanged between the routers. This flooding of LSAs significantly impact the operation of OSPF, and if every router in a multi-access network had to flood and acknowledge all receive LSAs to all other routers on the same multi-access network, the network traffic would become quite chaotic. In other words, it's going to get bogged down and it's going to have some overhead. This is why the DR, the designated router, and BDR, the backup designated router election is necessary. On multi-access networks, OSPF elects a DR to be the collection and distribution point for LSAs sent and received. A BDR or backup designated router is also elected in case the designated router fails. So that would cover the summary for everything that we have covered in this lecture. If you like these type of lectures, please thumbs up this video and subscribe to my channel. I know I went through this lecture a little bit too fast and I haven't gone through any of the lab materials and or explain OSPF in depth using lab examples. So stay tuned. I will post those in next few weeks. Until next time, good luck with your exams and have a nice day.